Hello students, last time I started the chapter Chemical Equilibrium. Today we will continue that chapter. So we'll start with the link between the chemical equilibrium and chemical kinetics. Link between the chemical equilibrium and chemical kinetics. Now if Kf is greater than Kr, then Kc is very large. What is Kf? Dissociation constant of forward reaction, and Kr is the dissociation constant of reverse reaction. If Kf is greater than Kr, then Kc is very large, and if Kf is approximately equal to Kr, that is rate of dissociation constant of forward reaction is approximately equal to the dissociation constant of reverse reaction. You know this relation, Kc is equal to Kf upon Kr. Now, if this Kf is approximately equal to Kr, then Kf and Kr have comparable values. They have comparable values, means nearly same values. Therefore, Kc, this ratio will be approximately equal to 1. Kc will be approximately equal to 1. Secondly, if Kf is greater than Kr, then reaction goes almost to completion because the dissociation constant of forward reaction is greater than the dissociation constant of reverse reaction. So reaction goes almost to completion. Next, you can say that again Kf, if it is greater than Kr, then if Kf is much larger than Kr, or you can say if Kf is much larger than Kc, the reaction may be irreversible. That is, reversible reaction is too slow to be detected. So the reaction may be irreversible. If Kf is approximately equal to Kr, now these two values have comparable values, mean nearly same values. So this ratio Kf upon Kr, that is Kc, will be approximately equal to 1. Secondly, you can say that reaction never goes to completion. And thirdly, you can say that comparable concentration of reactants and products are present at equilibrium. So in this way, you can give the link between the chemical equilibrium and chemical kinetics. Now we'll discuss about the Le-Chatelier's principle. First, we'll see the statement of this Le-Chatelier's principle. The question may be asked you the statement of Le-Chatelier's principle. What is the statement of this principle? Statement is given as when a system at equilibrium is subjected to a change in any of the factors determining the equilibrium condition of a system, system will respond in such a way as to minimize the effect of change. So this is the statement of Le-Chatelier's principle. Now we'll discuss about the influencing factors of the Le-Chatelier's principle. The first factor is the change of concentration. We'll discuss what is the change of concentration on the Le-Chatelier's principle. Consider this reversible reaction, that is formation of ammonia from nitrogen gas and hydrogen gas. You can write the reaction as N2 gas plus thrice H2 gas gives twice NH3 gas plus some amount of heat will be released. Now you know that at equilibrium, QC is equal to Kc. At equilibrium, Qc is equal to Kc. So you can write the expression for Kc as Kc is equal to concentration of ammonia gaseous raised to 2, that is a square, divided by concentration of nitrogen gas into concentration of hydrogen gas raised to 3, that is cube. Now if equilibrium is disturbed by making Qc less than Kc by adding some amount of hydrogen gas, Now, due to addition of extra hydrogen to the system is no longer will be at equilibrium. The forward reaction occurs to large extent than the reverse reaction until the new equilibrium is established. This results in increased yield of ammonia gas. So this is the effect of concentration. Second factor is the effect of pressure. You know the general gas equation is PV is equal to nRT. So you can write as P is equal to RT N upon V. Therefore, P is proportional to N upon V. You consider this first reaction, that is N2O4 gaseous. This is the colorless gas. It gives the product NO2 gas, which is a reddish brown gas. This is reversible reaction. Forward reaction takes place with increase in number of the molecules. If you observe this reaction, you can observe that the forward reaction takes place with increase of number of molecules. That means from one molecule of N2O4, we are getting 2 molecules of NO2 gas. So there is the increase in number of molecules in the forward reaction. Whereas the reverse reaction takes place with a decrease in number of molecules. Now you can observe the change in color intensity in this reaction. First we will discuss this change in pressure. The next factor, change in color intensity. And lastly, shift in equilibrium position. What is the shift in equilibrium position? Now first suppose if you decrease in pressure, if you decrease the pressure during the reaction, what will be the change in the color intensity? The color darkens. And what will be the shift in equilibrium position? The equilibrium shift to the right, the side with more molecules. Is it clear? Secondly, if you increase the pressure, what will happen? The color lightens to almost colorless. And what will be the shift in equilibrium position? To the left, the side with less number of molecules. So this is the effect of pressure. Second example, we will consider the reaction. H2 gaseous plus I2 gaseous gives twice HI gaseous. Now, as there is the same number of molecules of gas on both sides, change of pressure has no effect on the equilibrium, as there is no change in the number of molecules. That is, there is the same number of molecules of gas on both sides of the reaction. So you can say that a change of pressure has no effect on the equilibrium. Next, we will discuss about the effect of temperature on the equilibrium. A change of temperature alter the value of equilibrium constant, K. The equilibrium constant for exothermic reaction decreases as temperature rises, and that of endothermic reaction increases with temperature. An increase in temperature favors an endothermic reaction, and decrease in temperature favors an exothermic reaction. Now you consider this reaction, that is N2 gaseous plus thrice H2 gaseous gives twice ammonia gas and 92.2 kilojoules. Now you can observe that the forward reaction is exothermic and the reverse reaction is endothermic. The decrease in temperature favors the forward reaction as it is exothermic. Now we'll discuss about the effect of catalyst. Now addition of catalyst to the reaction at equilibrium increases the rate of forward and reverse reactions equally. Catalyst does not affect the equilibrium constant. And the effect on the composition of a reaction mixture. Now, in this tabular form, we'll discuss all these four factors. The effect of concentration, pressure, temperature, and catalyst on the position of equilibrium and the value of Kc. First, we'll discuss about the concentration. Effect of concentration. What is the effect of concentration on the position of equilibrium? If the concentration changes, the position of equilibrium also changes. And what will be the change in the value of Kc? There will be no change in the value of Kc. Is it clear? So this is the first factor, concentration. Second factor, we'll discuss about the pressure. Now, if the pressure is changed, it changes. The position of equilibrium also changes. If reaction involves change in number of gas molecules, if there is the change in the pressure, then position of equilibrium also changes. But what is the condition? If the reaction involves a change in number of gas molecules. What can you say about the value of Kc? There will be no change in the value of Kc. Third factor is the temperature, effect of temperature. If the temperature changes, the position of equilibrium also changes and the value of Kc also changes. And last factor is the catalyst. What is the effect of catalyst on the position of equilibrium? There is no change on the position of equilibrium by using the catalyst. And what is the effect on the value of Kc by using catalyst? There is no change on the value of Kc by using the catalyst. Now we'll discuss about the making of ammonia, or production of ammonia by Habers process. You know that the ammonia is produced by Habers process by using this reaction, by using nitrogen and hydrogen gas. Now, when nitrogen and hydrogen gas combines, it gives ammonia gas by this reaction. So this is the block diagram of the Habers process. Here nitrogen from air is taken and hydrogen from natural gas is taken. Both combines. The condition is the proportion of the volume is 1:3. Nitrogen and hydrogen, proportion of their volumes is 1:3 by volume, nitrogen and hydrogen. The conditions are 400 to 450 degrees centigrade and the pressure 200 atmosphere, and iron is used as a catalyst. Now gases are cooled and ammonia turns into liquid. And at the bottom there is liquid ammonia, so you can drain it out, the liquid ammonia from the bottom. And on the left hand side, the unreacted gases are recycled. So this is the production of ammonia or manufacture of ammonia by Habers process. Now we will discuss the industrial application. First we have seen just now, that is in the Habers process, industrial preparation of ammonia by this chemical reaction. Now this reaction proceeds with the decrease in number of moles. That is delta N is equal to -2. That means 1 plus 3. From the 4 moles of reactants, you are getting 2 moles of products. So there is decrease in volume of the number of moles. The value of delta N, you can change in number of moles as -2. And the forward reaction is exothermic because some amount of heat is evolved during the formation of ammonia gas. Now, iron containing a small quantity of molybdenum is used as a catalyst. First, we will discuss about the effect of temperature. The formation, if ammonia is exothermic reaction, hence lowering of temperature will shift the equilibrium to right hand side. At low temperature, the rate of reaction is small and longer time would be required to attain the equilibrium. So the optimum temperature is about 773 Kelvin. Second factor is the effect of pressure. The forward reaction is favored with high pressure as it proceeds with decrease in number of moles. Therefore, optimum pressure needed to be used, which is about 250 atmosphere. Okay, with this we have completed this chapter.